You're currently in South Seas CDF for the session Bypass Control Flow Guard Comprehensively by Yunhai Shang. Thank you.
Okay. Hello, everyone. Thanks for joining this talk. My name is Zhang Yunhai, and this talk is about Control Flow Guard, or CFG for short. First, let me introduce myself. I came from Beijing, China, and I work for NSFocus as a researcher and mainly focused on exploit detection and prevention. Now this is the agenda. First is a quick overview, and then CFG internals and attack surface. After that, I will show a universal bypass technique, and then finally the fix of that issue. Okay, this is the overview. Control flow guard is a mitigation that prevents redirection control flow to unexpected location. It's not a brand new feature. It was first introduced in Windows 8.1 preview, but disabled in RTM for compatible reason. And then Microsoft enhanced that feature and enable it in Windows 10 technical preview and Windows 8.1 update 3. Now the next is CFG internals. Since MJ0011 and Jack Tang has discussed this in greater detail, so here I just show some key points. When a module is compiled with CFG enabled, the compiler will append 5 load configure table entries. The first is for the address of a function pointer, which names the guardcf check function pointer. And the second one is resolved. The third and the fourth defines a table, the guardcf function table. Now this is an example of that table. It's a RVA list. The compiler will analyze the program and find every location that enemy indirect jump will arrive, and store those info in this table. So this is what the valid target address. And the compiler will also inject a check to ensure that the target address is valid. This is the function before CFG enabled. And this is the compiler code after CFG enabled. You can see those in red are injected code. It calls a function. This is the guardcf check function I mentioned before. Where CFG enabled mode is loaded, the operating system will map a bitmap into the processor's memory address space. It calls the CFG bitmap. It was used to track all valid target address. And the address of the bitmap itself is stored in NTDLL in the LDR system DLL initial block at offset 60, and its size was stored in the offset 68. When the module is loaded, the operating system also updated the CFG bitmap. It uses the guard-cf function table I mentioned before to update the bitmap. There is a little trick. Each odd bit in the bitmap will represent one 0x10, a legit address, and the even bit in the bitmap will represent the other 15 address. So the compiler will try to make most function alleged. So in most cases, each bit set in the CFG bitmap will represent only one address and not multiple address. Besides that, the operating system also updated the check function pointer and pointed it to the NTDLL LDR valid user call target. So at the runtime, this function will be called just before any indirect call. In this function, it will test the target address and to see is the address valid. This is how it tests the address. It will use the highest 24 bit of the target address as the index and treat the CFG bitmap as an array of 32-bit integer. So this can get one 30-bit from the CFG bitmap. And then it uses the third to the 8th bit from the target address as offset and test if the address is a legend. If not, it will or the offset with 1. So this is the little trick I just mentioned. Use this offset, it will fetch 1 bit from the 32-bit from the CFG bitmap and test if that bit is set. If so, the target address is valid and it will return to call the indirect call. Otherwise, it will raise an exception and close the program. This is how the function raises the exception. It will do more checks of the environment. If the process execute flag was set enable or ATL trunk emulation, or the protector is enable is executable, it will raise the exception. Otherwise, it will return true. Now that's the key point of the safety internals, which will be very important in the bypass technique. After that, I will discuss the attack surface of the CFG. I will discuss 5 attack surfaces. First is non-CFG modules. As any compiler involved mitigation feature, modules that are not compatible with those features enabled will always be programmed. For CFG, non-CFG modules has two effects. The first, it will contain unprotected indirect core. Of course, since it didn't compile with CFG enabled. So any direct core in that module will be unprotected. And if those indirect core can be controlled, CFG can be bypassed from that. The second effect is that all bits in that mode will have the corresponding bit set in the CFG bitmap. So all the address in that module will be valid. So you can get RP from those modes. But any compiler involved mitigation feature, non-CFG modules will exhaust eventually, since vendors tend to compile new modules with CFG enabled. So there will be less and less non-CFG mode. The second attack surface is JIT generated code. Because JIT generated code is just like non-CFG modules. If it contains indirect core, it's unprotected. And all bits in the generated code, the corresponding bit was set in the CFG bitmap. So just almost the same as non-CFG modules. But Microsoft is continuing to improve CFG protection. So both are not longer the case in the latest version of Edge, the default browser of Windows 10. In that version, JIT code is instructed, and JIT code pages do not have all bit set. Only few really indirect core target will have their bit set. So this will not be a problem for a long time. I think Microsoft will do this in other modules that will generate JIT code. The third attack surface is indirect jump, because this can redirect control flow just like indirect core. And this is an example of an indirect jump that can be fully controlled. And for this special one, Microsoft has added protection in Windows 10 for at least this special one. There can be other indirect jump not protected, but I think as time goes, Microsoft will protect all the indirect jump as indirect core. So this will be a problem for a long time. This won't be a problem for a long time. The fourth attack surface is return address, because this can also redirect control flow, but it not like indirect jump. It can't be protected use the same technique as indirect core. So this maybe this can be a problem for a long time. Maybe you know, traditional Stack Overflow are not usable nowadays. So we need a new technique to overwrite the return address. If you have the whole address space read-write capability, we can do this. First, we search for the stack, and then we search in the stack for an appropriate frame, and then replace the whole stack frame with craft1, and wait it to return to our special code. As far as I know, this will not be protected by Microsoft, at least for will not be protected recently. Now this is the last attack surface, the valid API functions. There's some API functions which can be used to exploit directly. The first three was can be used to switch the context, so you can control the EIP register completely. And the fourth and the fifth one can execute an executable directly, and the last one can load an library. You may notice that I marked the first three in red. This is because these functions are no longer valid interactive code target. So the usable are only three left, and I think this will be shorter and shorter, and this attack surface will not be a problem for a long time. Now, next I'll show you the universal bypass technique. The objective of the universal bypass is to bypass CFG comprehensively. That is to say, when we use this technique, we can make any exploit technique that be mitigation by CFG exploitable again, as there is no CFG. How could you do that? Let's review how the guard self check function is called. It's called through a function pointer. That is to say, it's a interactive code itself. So, if we override this function pointer, we can do some interesting thing. Let's see the behavior the check function do when the target address is valid. This is the instruction it executes. You can see from the aspect of the caller, this instruction has no difference with only a single return instruction because it has no return address checked. So if we overwrite the guard self check function pointer and point it to the single return, any address it tests will be valid, and we can overwrite the indirect code with any address as before. So this is our new objective, to overwrite the guard self check function pointer. But there's a big problem. The function pointer is read-only, so access denied. So we had to a new objective to make a read-only memory writable. That's the magic here. It seems to be crazy since we cannot execute code now because we haven't bypassed CFG now. But after some research, I found an interesting class in JavaScript 9. That's the custom heap. JavaScript 9 uses the custom heap to manage its custom memory. This is the structure of that class. You can see that it has many lists in the heap. From the offset 64 to the offset EC, there's many double linked lists. We can call the buckets. Each bucket is a double linked list of custom heap page. Oops. When this class is destructor, it has some interesting behavior. Now this is the function it will call. First, the destructor will call freeWall to freeWall the memory it allocated. And the freeWall will call freeBucket for each bucket it has. FreeBucket will call ensure page read write for each page in the double linked list. Now this is the key point. Ensure page read write will call auto protect with the following arguments. You can see the new protect is page read write. That's just what we need. So if we can control the arguments, the first arguments, we can make any page we like to be writable. Now the first question is, where can we find the custom heap? The custom heap is a member of the interpreter trunk emit at offset C. And the interpreter trunk emit is pointed by a member of JavaScript context at offset 4B0. And this is not a fixed one across versions of JavaScript, but I think it only have changed once. So for the early version of JavaScript 9, this may be maybe an offset a little larger. And JavaScript context is pointed by a member of script engine at offset 4. Next, script engine is pointed by a member of script set at offset 4 too. Script set is very easy to be located. You can choose any object you like that has a pointer, has a member pointer to it, and put it in an array you can predict to read the address. So we can locate the custom heap Let's review. Let's review the structure. When we locate the custom heap, we can search the double linked list, search the buckets, and find the appreciated one to modify, to overwrite is to modify the one page in that list. And try to trigger the destructor, so we can wait the destructor to make the page we chose writable. But when we reach the destructor, we will find that all the buckets are empty. The one we chose and overwrite is not there. Why? Because all custom pages are decommitted in JS Suite context closed, and the decommitted custom heap page is removed from the bucket. That is the double linked list. And the function JS Suite context close is called before the destructor. So when we reach the destructor, all the buckets will be empty. We overwrite the one we overwrite is no longer there. To resolve this, we have two choices. The first is to insert a fake custom page into the bucket. Since it is faked, it will be decommitted and will survive will survive to the destructor. And the other solution is to prevent the one we chose to overwrite from being decommitted. That is to modify some flag in the custom heap object to retrieve this. So now we can make any read-only memory writable. That is to say, we can overwrite the guard self check function pointer with anything we like. That is to say, we can bypass CFG comprehensively. Next, finally is the fix for that issue. This is the timeline. We report this issue to MSRC at January 22, and it was confirmed in January 30. And since the capability to make any read-only memory page writable is very essential, so Microsoft fixed this issue very quickly and released the patch at March 10. Very nice work. Now let's see how Microsoft fixes this issue. In the patch, it introduced a new function. The heap page allocator protect pages is a wrapper of the function auto protect. In this function, it will check the arguments before it called the auto protect. The check including the following. First, the LP address must be a legend. Next, the LP address must bigger than the segment's address. And the LP address plus the DW size must less than the segment address plus segment size. That is to say, the range of the core, the memory range of the core must be inside the segment. And the DW size must smaller than the region size. The last one is the key point. This function protect pages has an argument I call it the expected protect. It will check the memory region's origin protected and check if it is equal to the expected protect. Any check of this field, it will raise an exception and close the program. Now let's see the ensure page read write function. It will call the protect pages instead of virtual protect. And it will set the expected protect to page execute. That is to say, it only allows us to make an executable page to be read-writable. No longer any type. So we can't make the read-only one to be writable. That's how Microsoft fixed this issue. Very effective. Now, the last is some sound bias. The first is no save bullet. CFG is very good, but still not good enough, and and can be bypassed. The second one is read-only is not equal secure. You can see the GuardSafe function is read-only, but it's not secure. It can be overwrite. The last one is control the date, control the execute. You can see we only control the custom heap, the buckets of the custom heap. We can control how it execute and let it make what we want. So that's all. Any question?